All right, let's begin with the quick review here. The question says that the copper calorimeter of heat capacity 400 joules per Kelvin contains 0.4 kilograms of water of specific heat capacity 4,200 joules per kilogram per Kelvin at 20 degrees Celsius. If the water is warmed up to 30 degrees Celsius, calculate the amount of heat that is supplied. All right. So in this question here, I need you to identify two things. One, we are talking about heat capacity, and then also talking about the specific heat capacity. Remember last time we said that heat capacity and specific heat capacity are different. Heat capacity is for the whole mass of the body. Specific heat capacity is for 1 kilogram mass of a body. And you should always even look at the units. Yes, you should always even look at the units. Look at this one here, joules per Kelvin. Even if they have not told you that it is heat capacity, just know that joules per kilogram is the SI unit of heat capacity. So that is heat capacity. Likewise, joules per kilogram per Kelvin, that is for specific heat capacity. All right, to begin with, the question says that we have a copper calorimeter. In other words, we have like a container and then having water. So we shall simply say that heat supplied, remember the other equation that we had last time, heat supplied is always equal to the heat gained, so long as there is no heat lost to the environment, heat gained. That is where you should always begin from. Assuming that there is no heat lost to the environment, that's where I begin from. So in the question we ask ourselves that what is supplying the heat? They have not talked about it, but they're simply saying that calculate the amount of heat supplied. And what is gaining the heat? There are two things. One, the calorimeter, and then plus the water. Those are the two things that gain that amount of heat. So in our equation, we shall simply say that for the calorimeter, we have mass of the calorimeter, specific capacity of the calorimeter, times the temperature change. I can call it theta 2 minus theta 1. Then plus for the water, we shall have mass of water, specific capacity of water, times theta 2 minus theta 1. The temperatures are the same because they're all in the same container. We assume that the temperature of water is the same temperature of the container. So that is what we have. And then when you reach this step here, remember that heat capacity is equal to mass times the specific heat capacity. So for the calorimeter, we shall simply substitute the whole of this with what we have as the value of the heat capacity. So we shall say that this is the same as 400 into brackets 30 minus 20 plus 0.4 times 4200 times 30 minus 20. So what do we get there? We shall be having 400 times 10, which is 4,000. Then plus 0.4 times 4200 times 10. That will give us 16,800. And therefore, when you add the two, we shall get our answer as 20,800 joules. And that is our answer.
You're supposed to put for
So
the
you
calorimeter.
can do the corrections there because I see your answer was 16,800. Yes, you had forgotten it. So you can do corrections. So now let's go to our lesson. today, and that is all about latent heat. Latent heat. We talked about the word latent, and we said that it simply means something happens, but you don't actually notice that it is happening. You only see what you call the changes of state. In other words, if it is a solid, it turns to a liquid. If it was a vapor, it turns to a liquid, like that, changes of state. So we said that we give a scenario whereby in case you have a solid, and maybe you have a thermometer inserted into that solid, or you have water, maybe at 20 degrees Celsius. In case you warm that water until when it boils, when it reaches the boiling point, the temperature does not increase any further. If it is water, it remains at 100 degrees Celsius. You're supplying the heat, but then you're not seeing any change in temperature. So it means that at that point, the amount of heat which is supplied is apparent heat. It is latent heat. It is only causing the change of state of the substance. So, like we said last time, we have terms that we're going to use here, and among those terms, of course, the first one is what we call the latent heat. Latent heat. And then another one is called the specific latent heat. Specific latent heat. And then after looking at these two terms, we shall then go and look at the actual latent heat. In other words, the changes of state. Last time we said that we have three states of matter. We have solids, we have liquids, and then we have the gases. Like that. We said that the change of state from solids to liquids is what?
Melting. Melting.
It is melting, correct? Melting. And then going backwards, that is
Freezing.
Freezing, correct? Freezing. And in case you have a liquid turning into a vapor, then that is vaporization. And then turning from a gas back to a liquid, then that is condensation.
Condensation.
Yes. So we shall talk about terms that are going to combine these two. For example, melting and freezing, we talk about the specific latent heat of fusion, or simply the latent heat of fusion. To a gas, or from a gas to a liquid, we call that one the latent heat. I mean, it is the same amount of heat which is supplied, whether vaporization or condensation. We call it the latent heat of vaporization.
Yes.
We're going to see this later on. So let's begin by defining these two terms, latent heat and then the specific latent heat. Remember last time we said that whenever we see the word specific in heat capacity, it means that for 1 kilogram mass of a body. So how do we define it? So we define the latent heat. Remember, the latent means apparent, something which is known, which cannot be seen with your eyes. It is occurring, but then you cannot see it with your own eyes. So we say that latent heat is the amount of heat changes in the temperature. In other words, at constant temperature. Two things. We need to see that there is change of state and then there's constant temperature. Those two phrases must be in your definition. In case one of them is missing, then you are wrong. Likewise, specific latent heat, this is the amount of heat required to change the state of a 1 kilogram mass of a substance at constant temperature. So for this one, there are three phrases or three sentences. Change of state, 1 kilogram, and then constant temperature. So that is how with the minimum terms that we use. So after having defined those two, we're going to define the third one and then the fourth one as far as specific latent heat is concerned, and that is the specific latent heat of vaporization and the specific latent heat of fusion. We have said that fusion, the amount of heat that is gained or lost when a body is melting or freezing is the same amount of heat. The amount of heat needed here, whether it is melting or freezing, it is the same amount of heat. And we call that on the specific or the latent heat of fusion. Likewise, the amount of heat that is needed to vaporize a liquid or to condense a liquid is the same in size. So here we use the word vaporization. This is what we use. It's the same amount of heat. So whenever a gas is changing to a liquid, you shall be using specific latent heat of vaporization. But of course, it shouldn't confuse you. The word vaporization strictly means change of state from liquids to gases. So let's define these other two terms. Number 3, specific latent heat of vaporization. You write it in full. Vaporization. And then 4, specific latent heat of fusion. So how would we define this? You can write this. So specific latent heat of vaporization, specific latent heat of vaporization. We're saying that it is the amount of heat energy needed to change a 1 kilogram mass of a substance from liquid to gaseous state. Definition, what you're simply adding on is simply change of state from liquids to gaseous state.
Yes.
Or from a liquid to gas. That is what we are adding on. If you look closely at this statement, if you look closely at number 2, this one here, simply changing, we're simply adding on something here. Instead of talking about only change of state, we are specific on what change of state that is. So it is from liquid to a vapor or to a gaseous state. So likewise, for the latent heat of fusion, we're going to write the same thing, the same words. And when we reach change of state, we'll simply write from a liquid state to a solid state. So that is the same. So after looking at those definitions, of course, we said that the S amount of latent heat is a joule. It is the amount of heat needed to change the state of a substance at constant temperature. So there's nothing like mass, there's nothing like temperature. It is just a joule. It is a quantity of heat. And then for the specific latent heat, whether it is for specific latent heat of vaporization, which is LV, or whether it is for the specific latent heat of fusion, which is LF, it is the same SI unit. SI unit of specific latent heat is the joule per kilogram. Joule per kilogram. Simply because we're talking about the amount of heat only for 1 kilogram per kilogram. Temperature doesn't change, it remains the same. Okay, let's have some equations that we use here. Equation is used. Equation is used. You can say for vaporization, quantity of heat for vaporization or condensation. Hope that you remember those terms there, what each of them means. So quantity of heat is given by heat supplied or gained is equals, it is given by MLV. And then 2, for fusion, that is for melting or freezing. In other words, for fusion, the amount of heat is always given by MLF. Only that. There's nothing else. Where M is the mass, LV is the specific latent heat of vaporization, and LF is the specific latent heat of fusion. So I'm saying that we're talking about amount of heat which is supplied or which is gained. Let me ask you a question here. Let me first go back a little bit here. If a substance, let me first rub off this. If a substance is turning from a solid to a liquid, in other words, this point here, melting, do we talk about heat being supplied or heat being gained? Is it heat gained or lost?
It's turning from solid to liquid.
Yes.
Heat is gained.
Yes, very good. For a substance to melt, it must absorb the heat and then it melts. Correct. So which means therefore that if a substance is freezing, then it means that it is losing the heat.
Losing the heat.
It is losing the heat. Likewise, if a substance is vaporizing, turning from a liquid to a gas, it means that it has gained heat. It is gaining heat. It is absorbing the heat.
Yes.
And at the same time, if the substance is changing from a gas or from a vapor to a liquid, in other words, when it is condensing, it means that it is losing the heat. So that's why in this equation here, I'm having something like heat supplied or heat gained. So it is the same thing, depends on what our change of state is happening at the time. Okay, let's have some 2, 3, 4 examples about this. So examples, number 1. Examples. Let me first pause here. Yes, that is our question. The question says that 2 kilograms of water are heated and vaporized, in other words, at boiling point. So the question says that calculate the amount of heat supplied in order to boil off all the water. And in brackets, they're telling us that this specific latent water is 2.26 times 10 power 6 joules per kilogram. So, what do we do there? In this question, there's only one thing that is happening, and that is boiling state. So the amount of heat which is supplied whenever a substance is changing state from a liquid to a gas or to a vapor is given by MLV. Only that. So we have the mass, we have the specific latent heat of vaporization, which is 2 times 2.26 times 10 power 6. And our answer will be equal to 4.52 times 10 power 6 joules. And that is our answer. As simple as that. Let me check that answer whether correct or wrong. You can check it as well. All right. Let's have question number 2. A similar question this time around. I'm going to change something. just going to change something small. Can have it. That is 100 grams is calculate the amount of heat lost by steam while condensing. But it requires only one process, which is condensing. In other words, from a vapor to a gas. I mean, from a vapor to a liquid.
Okay.
Liquid. So likewise, we've been given mass, we've been given the specific localization, which is the same heat is not during function for 1 mass of a day. So don't get confused with this. So we shall say that amount of heat is given by MLV. Of course, you change your 400 grams divided by 1,000, which gives us 0.4 kilograms. Of course, at this level, we must be knowing that. So likewise, we shall say that our mass is 0.4 times 2.26 times 10 power 6. And the answer that you get will be in joules. Can you complete that? Okay, let's go to the next question here. Number 3. 400 grams of water freezes at 0 degrees Celsius. Calculate the amount of heat given out during the freezing, while freezing. So for this one, it is the same thing. We shall simply say that our quantity of heat is given by this time around is fusion. So have the mass is 400 grams, change it to kilograms, then times 3.36 times 10 power 5. The answer that you get will be in joules. So the specific fusion, when ice is melted, the fusion. So that is our question 3. Now we're going to advance a little bit. We're going to have 2 steps in the same question.
Yes.
We're having 2 steps in the question. The first get the answer to this, number 4. There's nothing much about. So now say water is heated until it all evaporates. The amount of heat needed to boil off all the water. So in the process of making the fixture of water and the specific distribution of water is going to be per kilogram. So what do we do? We're going to notice that there are 2 things that are happening. I remember that I said that always what we should do is to identify in our question what is supplying the heat and then what is gaining that heat is equal to mass gained. So what does that heat gain do? It is going to do 2 things. Heated until it all 200 grams of water at 30 degrees Celsius. I missed it out. Add it there. So 200 grams of water at 30 degrees Celsius is heated until it all evaporates. Calculate the amount of heat needed to boil off the water. So 2 things are going to happen here. The first one, this water is going to be warmed, or it's going to be heated from this temperature until when it boils. Until when it boils. In other words, the temperature is going to change. So at one point, the temperature is going to remain a maximum that is at boiling point, and then it will start to change state. So those are the two processes now. So we shall say here, it gained in increasing temperature, can say warming, and then plus evaporation. That is what the supplied heat does. So if you have that, we shall simply then say that this is the same as M of water, C of water, θ2 minus θ1, then plus M, L, V, like that. So the question is, what is θ2? What is θ1? You can help me guess there. I'm sorry, I beg your pardon.
Will evaporate. Is that θ2 is θ2 is 30.
30. How about θ1?
Hey,
0. Okay. So the question says that
it all evaporates.
the water is, yes, the question says that the water has been heated from 30 degrees Celsius until when it all evaporates. In other words,
Hey, that's
the
θ1.
maximum temperature that is going to be recorded will be the boiling point of water, which is 100 degrees Celsius. So from 30 to 100, the water which is 100, then it will start to change the state. So that was
So
the question
θ2
which was just hidden to you. So this is the same as mass of water, 200 grams, that is 0.2 times 40. 100, 0.2 times 2.26 times 10 power 6. And whatever you get will be the answer. So that is how we do it. You need to know, you need to read the question and you understand. So you can complete that. Then I will give you one other question. So that is our answer, 510,800. Let's try one more question. So number 5 says that a calorimeter of mass 20 grams and specific capacity of 800 joules per kilogram per Kelvin contains 500 grams of water at 30 degrees Celsius through the water in the current Celsius. So if the specific latent heat of vaporization of abbreviated later known as LV, the vaporization of water is 2.26 and 10 power 6 joules per kilogram, calculate the mass of the steam condensed. So the reason as why we have such a question here is simply that I want us to reason together as you're working it out together. But remember, I said that the most important thing is for you to identify what is supplying the heat and what is gaining that. So when you analyze that question, they've told me information on that one was missing about what was supplying the heat. Remember, the heat is being supplied by the steam, and then the calorimeter and the water are absorbing the heat, which is correct. But steam is on 100 degrees Celsius, according to that question there. So what happens is when the steam changes to a liquid, what happens when it has condensed? It will become water at still 100 degrees Celsius, but still that water will be losing that heat. So in other words, this is what I mean. This is what I mean. As part of our solution, we shall say that heat lost is equal to heat gained. So what is supplying that heat? What is losing that heat? It is steam, or what we call condensing steam. Condensing steam Remember, when the steam has changed to water, it is still water at 100 degrees Celsius. So that water, two things happened. The steam changed back to the water, and then the water also started cooling. And then what is gaining that heat? That heat is being gained by the calorimeter and the water in the calorimeter. So we don't need to confuse the two. The water in the calorimeter and then the cooling water, those two things are different. So for the cooling water, shall use the mass of the steam because it is the steam which has condensed the water. And for the water in the calorimeter, that was given as 20 grams, which is 0.02 kilograms. So here we shall say times the specific latent heat of vaporization, the mass of steam, which has now turned to water, times the specific capacity of water, because it is now water, then we have temperature theta3 minus theta2. This is equal to, we talked about those two temperatures, theta3, theta2, and then theta1. So for the calorimeter, we have mass of the calorimeter, specific capacity of the calorimeter, times theta2 minus theta1. Then plus mass of water, specific capacity of water, into theta2 minus theta1. So that for the water in the calorimeter and the calorimeter itself are always at the same temperatures. So we have steam. Let me first write this from here. We have steam at 100 degrees Celsius. We have water in the calorimeter plus the calorimeter is 30 degrees Celsius. At 30 degrees Celsius. So as this one is supplying the heat, this one is gaining the heat. So at one point, the equilibrium temperature becomes 70 degrees Celsius. In other words, the temperature in the 100, our theta2 is 70, and then our theta1 is 30 degrees Celsius. Always we get a smaller temperature subtracted from the bigger temperature. That is what you need to remember always. Okay. So after understanding that, then you can substitute in our expression. We shall say that the mass of steam is unknown. Shall just use the letter M. Shall just use the letter M. So M times 2.26 times 10 power 6 plus M times 4200 into 100 minus 70. This one is equal to this one is equal to mass of steam, mass of the calorimeter, which was what was the mass of the calorimeter? It was 20 grams. 20 grams to 1,000, I mean to divide by 1,000, that will give us 0.02 kilograms times 800 times 70 minus 30, then plus mass of the water was 500 grams, which is 0.5 times 4200 times 70 minus 30. So with that, I needed to simplify it and get me I am waiting for the value of the steam. I'm waiting for you.
5 kilograms.
kilograms. All right, that is okay. That is fine. 0.55 kilograms. That is. I'm going to send you one question. Try it out, and then you get me the answer. I'm going to send it to you now after this. Then when we meet
Yes,
next
teacher.
week, we shall be looking at the graphs about the changes of state. There are some things that I've left out, like some of the experiments. I've left them out. We shall look at those ones while at school, but they're not very hard.
Teacher.
What normally confuses are the calculations. But once you get once you've got the calculations, you simply transfer the knowledge. Whatever we have been
Yes,
doing in the
teacher.
calculations, what we shall be doing in the experiments. Otherwise, allow me stop here and have a great day.
Likewise, teacher.